Today, in this video part, we will see Faraday's laws of electrolysis. Michael Faraday was the first scientist who described the quantitative aspect of electrolysis, in that the uses of electrolysis. Now, Faraday's law also flow from what he has been discussed earlier. So, Faraday's laws of electrolysis. After his extensive investigation on electrolysis of solution and melt of electrolytes, Faraday published his result during the age of 1832 to 34 in the form of the following well-known Faraday's two laws of electrolysis. According to the first law, the amount of chemical reactions which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte solution or melt. That means the amount of the chemical reactions occurs at electrode during the time of electrolysis by passing a particular amount of current depends on the quantities of the electricity passed. If you pass more quantities of electricity, the more chemical reactions occurs. Thereby, the electrolyte deposited or the electrolyte absorbed at anode or cathode depends on the amount of the electricity passed. If you pass more electricity, more amount should be deposited or more amount should be absorbed. This is what the first law. Mathematically, we can say first law W equal to QIT, where Q is the W equal to Q, this is equal to IT. That means where Q is nothing, your quantities of charge, and I is current and T is time. So like this one, this is the first law. In the second law, the amount of different substance liberated by the same quantities of electricity passing through an electrolytic solutions are proportional to their chemical equivalent weight. That is, atomic mass of the metal divided by number of electrons required to reduce the cations. That is, we call as a equivalent weight. So W1 by W2 is equal to E1 by E2. This is what in the second law. Now let us see there was no constant current sources available during the Faraday's time. The general practice was to put a coulometer for determining the quantities of electricity passed from the amount of metal deposited or consumed. However, coulometer was now absolute and we now have constant current sources available, and the quantities of electricity Q pass is given by Q equal to IT, which I would mention. So Q is the coulomb when I is the current in ampere and T is the time in second. The amount of electricity required for oxidation or reduction depends on the stoichiometry of the electrode reactions. Let us take one example of it. Ag plus, then means silver ions in the aqueous solution plus one electron, then you will get Ag solid. 1 mole of electron is required, means that since above the electron stoichiometric value is 1, so we can say that 1 mole of electron is required for the reduction of 1 mole of silver ions. So let us see the charge. Charge on 1 electron is equal to 1.6021 into 10 power minus 19 coulombs. So therefore, the charge of 1 mole of electron, that is equal to Avogadro number into one charge carried by one electron. When you multiply these two, you will get 96487 coulombs per mole. So the quantities of electricity which we get here, that is called as a Faraday, and it was represented by F. So approximately 1 Faraday equal to 96500 coulombs per mole. Now let us see one example related to this. In the example 3.10, a solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of the copper deposited at the cathode? And this question was already in the board examination. Here T equal to 10 into 60 is time is in the minute, so we need to convert into second. So 10 into 60, that we get as a 600 second. Charge Q equal to IT. Here I is 1.5, T is 600 seconds, so you will get it 900 coulombs. Now let us write the equation. So here you need to convert copper sulfate to copper. So copper sulfate means that copper ion presence. Now in the aqueous solution we will need to get 2 electrons, then you will get copper solid. Here in the stoichiometric value of E is 2, so we require 2 Faradays of electricity. So 2 Faraday means 2 into 96487 coulombs are required to produce 1 mole. 1 mole means above the copper in the product side, the stoichiometric value is 1. So 1 mole of copper, that is what? 63 atomic number of copper, that is what? 60. Atomic weight of copper, that is 63 grams of copper is reduced. So if you require this much amounts of coulomb, then we produce 63 grams. So if it is 1 coulombs, then the amount of copper deposited should be 63 divided by 2 into 96487. If it is of 900 coulombs of charge, then the amount of copper deposited should be 63 into 900 coulombs divided by 2 into 96487. That is unitary method, which is in your lower classes. The value which you get is 0.2938 grams. This is what about the amount of the mass deposited at the cathode when you pass an current of 1.5 ampere in an electrolytic cell for about 10 minutes. This is your answer. Now let us see about the products of electrolysis. The product of electrolysis depends on the nature of the material being electrolyzed and the type of the electrode being used. So that means the product depends on the nature of the material which to be electrolyzed and the electrodes which you are using. If the electrode is of inert electrode means which cannot combine, that is like platinum or gold, it does not participate in the chemical reaction and act only as sources or sink of electrons. So if you are using inert electrode, then the product depends on the nature of the substance electrolyzed, but not in the electrode, as it does not combine during the time of chemical reactions, or it does not involve during the time of chemical reaction. That is why products depends on the substance which to be electrolyzed. If you use another electrode, then the product depends on either the substance which to be electrolyzed or the electrode, as the electrode itself can join during the time of chemical reaction if it is not inert electrode. So if the electrode is reactive, then it can participate in the electrode reaction. Thus the product of the electrolysis may differ from that electrolysis product obtained during the time of using inert electrode. This is what we have. So the product of electrolysis depends on different materials. That is oxidizing and reducing species present in the electrolytic cell and their standard electrode potential. As we know here that the products depends on the oxidizing agent or the reducing agent present in the electrolytic cell and the current pass, that is what standard electrode potential. Some of the electrochemical processes, although feasible means also spontaneous, and are so slow kinetically at lower voltage, these do not seem to take place, and an extra potential, that is over potential, has to be applied, which make such process more difficult to occur. That means there are some electrochemical process which is possible only in the lower voltage. If higher voltage is applied, then the reactions is more difficult again. So like this we have some examples. Now let us take NaCl. NaCl, when electrolysis, then we get sodium metal and chlorine gas. Here Na get reduced to Na plus ions at the cathode. And chlorine, which is oxidized at the anode. During this electrolysis, the aqueous sodium chloride solution, the product is of sodium hydroxide, chlorine and hydrogen gas, which you have already done in your class 10 as a chlor-alkali process. Chlor-alkali process you have done. So the cathode reaction is as Na plus E minus give Na solid. Here electrode potential which you applied is minus 2.71 volt, and ice plus 1 electrons give half ice 2. Here electrode potential is 0. These two reactions occurs at the cathode. The reaction with higher value of E naught is preferred. Therefore, the reaction at the cathode during electrolysis is of ice plus 1 electrons give half ice 2. But ice plus in aqueous is produced by the dissociation of H2O. That means when H2O becomes dissociated, then you will get ice plus aqueous and OH minus aqueous. You will get ice plus aqueous and OH minus aqueous. So therefore, the net reaction at the cathode may be written as H2O plus E minus aroma half H2 plus OH minus. This is the anode. This is the cathode reaction in the electrolysis of your sodium chloride. Now at the anode, what are the reactions take place? That means at anode the oxidation reactions are possible. At anode, oxidation reactions are possible. So let us see the oxidation reaction. Chlorine minus this give, that means chloride ions in aqueous solution gives half of the Cl2 plus E minus. Here 2 times of H2O aroma O2 plus 4 times of ice plus along with 4 electrons. In the first, chloride to chlorine, the electrode potential is of 1.36 volt. In case of water to oxygen and hydrogen ions, then during the time your electrode potential which you applied is 1.23 volt. The reaction at the anode with lower E naught value is preferred, as in the anode we need to go oxidation. At the cathode we need to get higher E naught value is preferred. but in the anode, lower anode value is preferred. So out of this, the lower one is of 1.36 volt. So the overall reaction in the electrolysis of sodium chloride are as NaCl, then water, then you will get Na plus and Cl minus. At cathode, I is 2O plus 1 electron, then half of the I is 2 plus O is minus. At anode, Cl minus gives half Cl2 plus E minus. So if you add these two equations, then you will get NaCl plus I is 2O, arrow mark, Na plus O is minus plus half of the I is 2 plus half of the Cl2. So this is what we have in the electrolysis of sodium chloride. So next, let us see about the batteries. Let us see about the battery. We have two types of batteries. One which can reverse. That means the redox reactions occurs should be reversed. Then it becomes recharge. Those which can reverse are called as a secondary cells. Those cells, once the redox reactions occurs, after that the cell becomes dead, we call as a primary cells. There are two types of cell. One is primary cell, which once redox reactions occurs, the cell becomes dead. Another one, the redox reactions should be reversed again and again. That we call as a secondary cells. Secondary cells are rechargeable cells. Now let us see about the Nacl cell or dry cell, we can see. This is an example of primary cell. Now, this dry cell are also called as a Nacl cell. Dry cell are also called as a Nacl cell. Nacl cell. And generally, it consists of a zinc container. Nacl cell consists of a zinc container which acts as an anode, and the cathode is of graphite rod surrounded by powder manganese dioxide and carbon. The space between the electrode is filled by the paste of ammonium chloride and zinc chloride. The electrode reactions are complex, but they can be written as at anode, zinc lost electrons. So Zn goes to Zn2 plus and 2 electrons. At cathode, the mixture of manganese dioxide and ammonia gain 1 electron to get MnOOH plus ammonia gas. In this reaction at cathode, manganese is reduced from +4 oxidation state to +3 oxidation state. The ammonia produced in the reaction, form a complex with zinc to give tetraamino zincate. And the cell has a electrode potential of 1.1 volt due to the formation of tetraamino zincate complex compounds. The ions present in this cell become dead. Due to that, some cells without using also we get dead cells. Once the chemical compound, that is one of this ammonium chloride and zinc chloride, combine together to form this tetraamino zincate complex, then no more further reactions occurs. That is why the cell become dead. Now we'll go to the mercury cell. Mercury cell generally prefer for the low current devices like hearing aids or our hand wash, which consists of zinc mercury amalgam as an anode and the paste of mercury oxide and carbon act as a cathode. The electrolyte is the paste of potassium hydroxide and zinc oxide. The electrode reactions for this cell are as an anode. Amalgamated zinc gives plus 2 times of OH minus, then you will get zinc oxide, water and 2 electrons. At cathode, this mercury oxide plus water plus 2 electrons give mercury liquid and 2 hydroxide anions. The overall reaction for mercury cell is of ZnIg plus HgO give ZnO plus Hg. The cell potential is approximately about 1.35 volt, and this voltage always remains constant during its life, as the overall reaction does not involve any ions in the solution, whose concentration can change during its lifetime. So this cell is used as a lifetime device. Now we will go to the secondary cell, that is lead storage battery, which can be rechargeable by passing current. In a secondary cell, after use can be recharged by passing current through it in the opposite direction so that it can use again. Most important secondary cell is of lead storage battery. The most important secondary cell is of lead storage battery. It consists of a lead anode and a grid of lead packed with lead dioxide act as a cathode. And 38% solution of sulfuric acid is used as an electrolyte. The cell reactions when the battery is in use are given below, as at anode lead plus sulfate ions gives lead sulfate and 2 electrons. At cathode, lead oxide plus sulfate ions plus 4 times of H plus 2 electrons give PbSO4 plus H2O. The overall cell reaction is of Pb plus PbO2 plus twice H2SO4 gives PbSO4 plus H2O. On charging the battery, the reaction is reversed, and PbSO4 solid on anode and the cathode is converted into Pb and PbO2 respectively. That means the cathode and anode now interchange while the electricity is passed in the battery. Now you have seen this is lead storage battery. Another important cell here in your textbook is nickel cadmium cell, which has a longer life than lead storage cell but more expensive to manufacture. The electrode reaction during charging and discharging, let us see, cadmium plus nickel hydroxides give cadmium oxide plus nickel hydroxide plus water. This is what during discharging. During charging, the reaction become reverse again. Now, the remaining part, that is fuel cell and corrosion, was already deleted for this year, so we will not discuss these reactions as it was already deleted. And this is the end of your chapter electrochemistry. Thank you.